Hello everyone. In this video we are going to discuss about dependence of voltage on reactive power. To know how much the voltage is dependent on a reactive power, let us consider a source supplying a load as shown here. We are having a source voltage, the line impedance and a load. The voltage across load is mentioned as V. The total power is P plus jQ. This is a one line diagram that we are considered here. For this one line diagram, if we draw the phasor diagram, it will be like this. Here you can see the first phasor diagram is for lagging current and second one is for leading current. Here we can see the source voltage, load voltage and the load current. Here we are having IR, which is lagging, and here it is IX. Triangle OCD. Triangle OCD is a right angle triangle here. Okay. Here we are having a source voltage, load voltage and current. This is for phasor diagram with leading current. For this phasor diagram with lagging current, with respect to this triangle OCD, right angle triangle, if you apply Pythagoras theorem, the square of the hypotenuse E square will be equal to adjacent square into this. Okay, hypotenuse square is equal to adjacent and the base square. Here it is OC. OC consists of OA plus AB plus BC. OA plus AB plus BC whole square plus DC whole square, marking it as equation number 1. Okay, again mark this as equation number 1. As we can see from this diagram, OA is nothing but our voltage V. OA is nothing but our voltage V, and AB is nothing but IR cos phi. The angle subtended here is phi. To find out AB, IR into sin phi leads to AB, and BC is equal to IX sin phi. IX is the hypotenuse here, and the angle subtended here it is phi. So we will be having BC as IR sin phi, IX sin phi. Fine. Now we are having the value of OA, AB and BC, but we don't know the value of DC yet. So DC can be represented as DC is equal to DE. DC is equal to DE minus CE. DC can be represented as DE minus CE, where DE is IX cos phi minus CE is nothing but our B value. These two are perpendicular in nature, parallel in nature. You can take it as IR sin phi. To get AB, we'll be having IR cos phi. To get this line, we'll be having IR sine phi. This leads to DC. We got OA, AB, BC and DC values. Now we are going to substitute these values in our equation 1. After substituting these values in equation 1, we'll be having E square is equal to, within the bracket, OA is V plus AB is IR cos phi plus BC is IX sin phi whole square plus DC square is nothing but DE minus DC, DE minus CE, which is IX cos phi minus IR sin phi. This will be equation number 2. Here we can see we just substituted the value of OA, AB, BC and DC. Now we all know real power P is VI cos phi and reactive power Q is nothing but VI sin phi. If we rearrange this with respect to current I, we'll be having for first one, I is equal to P divided by V cos phi, or we can mark it as I cos phi as P divided by V. And here also, if we mark it for I sin phi, it will be Q divided by V. Considering these two as our equation number 3. If we substitute equation 3 in equation 2, substitute equation 3 in equation 2, we get E square is equal to V plus IR cos phi, or we can consider as I cos phi. I cos phi is nothing but P by V. R is there as it is. I cos phi is nothing but P by V plus X as it is. X as it is. I sin phi is nothing but Q divided by V whole square plus X as it is. I cos phi again marked as P by V minus R as it is. I sin phi as Q by V whole square, marking it as equation number 4. Now we have marked it as equation number 4. Therefore, E square is equal to V plus delta Vp whole square plus delta Vq whole square, marking it as equation number 5, where delta Vp is a small change in voltage that is in phase with V, R into P by V plus X into Q by V. This is in phase with the voltage V, whereas here you can see, here it was R into P by V, here it is X into P by V minus R into Q by V, which is a quadrature with the V. This part is in quadrature with the P, with the V voltage, so we mark it as delta VQ whole square, and this one is in phase with the voltage V, so we mark it as delta Vp, right? You can see this part comes for other than V, we will be having here we can see V is nothing but OA, and whatever this part is nothing but AB and BC, AB and BC, AB and BC, which we marked it as a delta VP. Here we have marked it as a delta VP, and this part, which is nothing but our DC, we marked it as a delta VQ. Here you can see we marked it as a delta VQ. Okay. If delta VQ is very much smaller than V plus delta VP, we are assuming if delta VQ is very much smaller than V plus delta VP, then the equation becomes E square is equal to V plus R into P plus X into Q whole divided by V whole square. Or if we take a square root on both sides, it leads to E is equal to V plus RP plus XQ divided by V, where RP plus XQ divided by V we mark it as delta VP. Okay, if we rearrange the terms as E minus V will be approximately equal to RP plus XQ divided by V, which is nothing but our delta VP. Mark it as equation number 6. Okay, we are marking it as equation number 6. Therefore, the arithmetic difference between the voltage E and V will be equal to RP plus XQ divided by V. If we neglect the resistance, okay, if we neglect the resistance, resultant will be E minus V will be equal to X into Q divided by V. Only if resistance is neglected. Remember, if resistance is neglected, E minus V equation 6 becomes this part becomes 0. We'll be left with X into Q by V, marking it as equation number 7. Okay, so from equation 7 we can say that the receiving end voltage V depends on reactive power drawn by the load. You can observe here the receiving end voltage V purely depends on reactive power drawn by the load at the receiving end bus. Remember, we are talking with respect to receiving end. If we continue with the same to analyze more, under short circuit, condition, the complex power at short circuit, SSC, complex power S at short circuit is given by SSC is equal to E into ISC, short circuit current conjugate. Okay, complex power will be equal to V into I conjugate, right? Similarly, for short circuit we will be taking it as E into ISC conjugate, which is approximately equal to V ISC conjugate, keeping that power remains the same from sending end to receiving end. We are assuming that will be equal to, if we replace ISC we'll be having V square by ZSC conjugate, marking it as equation number 8. Current is nothing but a V by Z. So V into V is V square by ZSC conjugate. If you again neglect the resistance part, neglecting resistance, equation 8 becomes SSC is equal to V square by X, marking it as equation number 9. Therefore, from equation 7 states as E minus V is equal to X into Q divided by V. This is also neglecting resistance. Here also we are neglecting the resistance. If we rearrange the terms, E is equal to X into Q divided by V minus V. If we take V common, E will be equal to, if we take V common, 1, sorry, here it is minus, if it comes here it becomes plus, V1 plus X into Q divided by V square. Therefore V is equal to E divided by 1 plus XQ divided by V square. Okay. Therefore V is equal to E divided by 1 plus Q divided by SSC. Here we can see SSC, short circuit power, is equal to V square by X. Here it is X by V square, which is nothing but 1 divided by SSC, which can be equated as, approximately equated as E into 1 minus Q divided by SSC. Only if Q is very much smaller than SSC. Only if Q is very much smaller than SSC, marking it as equation number 10. Okay. This we can get only by taking a complex conjugate. Okay. Multiply and divide by the denominator. To get this term, we need to multiply and divide by the complex conjugate of the denominator. For this, we'll be getting this one. Hope you know how to take the complex conjugate. If not, put a message on my comment box. I will detail the same. Okay. Equation 10 represents, which means V is equal to E into 1 minus Q divided by SSC, represents the approximate relationship between the voltage and the receiving end voltage, okay, and the reactive power in terms of short circuit strength. This gives the relationship between voltage at the receiving end and the reactive power. Receiving end voltage and the reactive power with respect to short circuit strength. This completes the relationship between dependence of voltage on reactive power. Okay guys, thank you. If any doubts, you can put a message on my comment box and I will go through it. Thank you.